To be able to distinguish a pair of enantiomers, we use an instrument called polarimeter. Looks something like this. This is a simple version of it. All right. So we have a light source, right? Point into any direction, pass through a slit, a filter. Actually, the filter where the slit is pointing up right there. Only the light source that, only the light that have the same plane with the slit can pass through. So this become a polarized light. We're gonna talk about in a bit. Pass through a compound sample, right? And it get turned and go through the analyzers. Okay. So how does it work? Let's start with right here. Lights. Could be a sunlight, could be a lamp, could be any light source, right? Lights normally consist of electric field and magnetic field. They are perpendicular, right? And we're gonna use that, just the whole thing here to show the direction of electric field, right? And unpolarized light have electric field pointing in any direction. That's pointing in any direction right there. That's we call an unpolarized light, right? Now we can convert an unpolarized light to a polarized light, which is just have one plane right there using a filter. Let's say we have unpolarized light pass through the filter. If the slit of the filter point up, the polarized light come out gonna point up, all right? And this polarized light will pass, or will travel and or get to the analyzer, which just think about another filter got a slit on it. If the slit have the same direction as the planar polarized light, it can pass through it. You can see it. Our eyes can see it. All right. But if you rotate, let's say rotate 90 degrees, now the slit is a perpendicular, not the same plane with the polarized light. Our eyes cannot see it. Okay. All right. This is how things work here. From the light source, okay, any light source. So we have an unpolarized light pass through the a filter that have slit pointing up. So only one plane of the polarized light will pass through. All right, and then we're gonna put a compound, a solution of the compound. For example, in this case, I use water. Water is a chiral, right? An a chiral compound does not do anything with a polarized light. Just polarized light can just pass through. Woo, look like that. Okay, so a chiral compound is optically inactive. It doesn't do anything with the light. Optic means light, right? If you have an analyzer, which is another filter, and the slit have the same plane with the polarized light, it passes through it, you can see it. All right. Now, replace this water with an let's say an enantiomer. Okay, a chiral compound. Not enantiomer, just a chiral compound. We have a solution of it, of the RR tartaric acid. All right. Now the light source come in, become a polarized light, and polarized light gonna travel and travel through this solution. Look what happened. It get turned. Right? It get turned. I don't know what the direction, but it get turned somehow. All right. So chiral compound is optically active. Right, the ability to rotate planar polarized light, so can rotate from pointing up, go to kind of diagonal. All right, and now we can observe it. In this case, the direction of the slit is not the same direction or same plane with the planar polarized light. You cannot see it. What you have to do, you have to rotate. This is like in the machine, in the instrument. You can. That's like a knob. You can rotate it. Right. And you can rotate it, make it the same plane, and thus you're going to start seeing some light coming out. Okay? Now, the angle right here, we call it observed rotation. Right? Observed rotation is the extent of rotation of a plane of polarized light, by the solution of chiral compound, right? But we don't really use the observed rotation because it depends on many factors. It depends on concentration. If the compound, the solution right here is really concentrated, the observed rotation is going to be large, right? Length of solution also affect how much the light get rotated, because there are a lot of compounds that the light has to pass through. Temperature also affect that. Light sources also affect it. I mean, there's just a lot of things that to affect. Imagine this: we use the boiling point to identify what the compound that is. Right? For example, water always boil at 100 degrees. Imagine though, if water has multiple boiling points. You'll be like, that doesn't make sense. Water is always boil at 100 degrees. Well, think about it. If you go up high in a mountain, let's say 10,000 feet from the ground, from the sea level, the boiling point of water drops, right? So one compound could have multiple boiling points. So that doesn't make sense, right? That doesn't make any sense. So we have to control the variable. All right, the boiling points. When we talk about boiling point, it has to be at the sea level. So one compound, we have only one boiling point. Does it make sense? All right, same thing right here. So the observed rotation depends on many factors right here. We can't really use anything with it. So we have to control this variable. Instead of using observed rotation, we're gonna take observed rotation value, plug into this equation, and what comes out is a specific rotation, which is the observed rotation at the standard condition. All right, so we like a sea level for the boiling point. The standard condition is the concentration is 1 gram per milliliter, right, and 1 decimeter length of the concentration, the path of the concentration. Right, so 1 decimeter is 10 centimeter basically. Right, so you plug in here, plug in the length, right, in decimeter, gonna be in decimeter, and concentration in gram per milliliter, not molarity. If you have molarity, you have to convert to gram per milliliter. Okay, and so it's super simple calculation there. This is the only time in the whole organic chemistry courses, like 1 and 2, that you're gonna use calculator, just right here. Okay, all right. All right, one more time. So, chiral compounds are optically active. They rotate the plane of polarized light. A chiral compound, no, they don't do that. Okay, all right, we're gonna practice together right here. All right, give me 1 second. 1 second. Okay, all right, do it on your own, and you're gonna check it with me. Okay, when 0.300 gram of S-naproxen is dissolved in a 10.0 milliliter of water, this two number gives you the concentration. You know, grams of solute, 10 milliliter of the solvent, and placed in small a sample cell 10 centimeter in length. That's give you, this is exactly 1 decimeter. Okay, the observed rotation is plus 1.99 degrees. I'm going to tell you what plus mean. Using the D line of sodium and at 20 degrees. So D line, which is sodium, as D line sodium as a light source, and at 20 degrees Celsius. Calculate the specific rotation of this compound, S-naproxen. Right? Oh, just plug in, super simple there. Observed rotation is plus 1.99 degrees. The concentration, the length is 1 decimeter, right? And concentration 0.3 gram over 10 milliliter. Here we go. Do the math there. Plus 66.3, right? So this is 3 sig fix, 3 sig fix. So don't forget about the significant figures, okay? All right, that's super simple there. So S-naproxen at this concentration rotate S-naproxen in general rotate the planes of polarized light by 66 degrees. All right. Let's go back to the original question. How do we distinguish or tell the difference between a pair of enantiomers? Right? They have the same property except the plane of the specific rotation. A pair of enantiomers. Let's go in. Okay, a pair of enantiomers have the same specific rotation. They are equal in magnitude but opposite direction. S-naproxen rotate the planes of polarized light counterclockwise, so negative, by 66 degrees. But R-naproxen do the same way, right? Do the same magnitude but clockwise, opposite direction. Okay, we have the term. So plus mean clockwise, negative mean counterclockwise. All right. We have another term, levorotatory, which means counterclockwise. I think it's an old term. Dextrorotatory, or D, that's clockwise, right? You probably have heard about D sugar, like D glucose, D fructose. That's come from D right there. They rotate the plane of polarized light clockwise. All right. And the S. L-glucose, which is enantiomer of a D-glucose, they rotate on the opposite, the light in the opposite direction. That's how you tell the difference. Okay. All right. Let's. Oh, by the way, one more thing you need to know: the plus minus sign right here rotate the planes of polarized light clockwise, counterclockwise, has nothing, no in relation with R and S system. R and S system is come up by human, by the scientists to determine how to call, how to name the enantiomers, a pair of enantiomers, right? How to name, not a pair of enantiomers, how to name the configuration of each chiral center. Has nothing to do with planar polarized light, totally different thing. Okay, plus could be an R, plus could be an S, negative could be S, negative could be an R. It has nothing to do with each other. All right. Okay. All right. Now let's moving on. We're gonna talk about racemic mixture.